Okay, so I want to lead up to the graph cut algorithm, and to understand it, we need well, one is really a prerequisite, and the other is more to know a little bit where terminology comes from. So let me start with terminology. You see pictured Peter Hammer, born in, I think, in 1936 and died a few years ago. He is one of the eminent figures in operations research. And in the 60s, he has found and shown results that made it to image processing only in the last decade. And then admittedly, the algorithms had to be tuned to make them run fast enough on problems involving millions of variables. But on the other hand, in image analysis, we have the advantage that oftentimes these variables are arranged in a Cartesian grid with sparse connectivity, so this problem structure can be exploited. However, the basic results that allow using these algorithms in the first place are due to Hammer and then his work with colleagues Boros and others. So I copied down from last time the MAP, the maximum a posteriori problem for a pairwise Markov random field. So we want to minimize with respect to a set of unknown variables x, this term here comprising unaries or data terms, and then pairwise or smoothness terms, and we express this in terms of a linear expression. However, we can also write directly a quadratic expression. And I'm not sure what is easier, if I should introduce the quadratic expression from scratch, or show how it can be obtained from this linearized version. If I want to obtain it from the linearized version, I can do it as follows, by saying that I want to specialize this now to the binary case. So for only a binary pairwise, there was the magic ink. For binary pairwise MRF, I can write that my indicator variable qi of 1 becomes xi, and my indicator variable qi of 0 becomes not xi, and then similarly for the pairwise terms, I can say that qij 0 becomes not xi times not xj, and so on. And if I insert all of the above in this energy expression, I get the following. My energy becomes a sum of unary terms, so I goes over the set of all vertices, plus contributions from all pairs of points where I is adjacent to j, or the edge ij is in the set of edges. Okay. Oh, that's wrong. Psi j of 1, 1 times xi xj. And if I really define x bar as done up here, then this is a function just of x, not of x and its inverse. And it is in this case a quadratic polynomial. In my points xi. With Booleanity constraints, so xi is in 0, 1, or the way Hammer preferred to write it, xi is in b. So we have here Booleanity constraints. And such a quadratic polynomial with Booleanity constraints is called a quadratic pseudo Boolean function. Why pseudo? Because Boolean functions themselves map from Boolean variables to Boolean variables, and here instead we map from a Boolean set, so we map from b to the n to the real set. Any pseudo Boolean function can be characterized in 3 ways. First approach is to say we simply have a value table, sometimes called a tableau, which simply is a lookup table. Okay, it's not very interesting. For each and every possible configuration of variables, it stores the resulting real value or the associated real value. More interesting is a representation in terms of a so-called posiform, where posi comes from positive. In this case, the energy, or so let me call this pseudo Boolean function E. In the posiform, E is written as a constant term, plus a linear term, plus a quadratic. I'll say in a moment what these U's are. and so on. This goes up to a n-fold nested summation. So these UIs are in either xi or in xi bar, which makes the whole thing here a function of the set of all original variables x, but also of their complement. Where I goes from 1 to n. So U is that, where Hammer calls these literals as opposed to variables. So literals for taking a explicit value. And all coefficients in such a posiform, all coefficients a0 I'm not writing them down explicitly because there are so many. So all these coefficients a are non-negative. Now this is a highly redundant representation. Redundant. As you can ascertain by simply looking at the number of coefficients there are. So the coefficients we have is 1 plus n squared plus n third, and so on. So this is roughly n to the power of n coefficients versus 2 to the power of n entries in the value table. And the consequence is that the representation is not unique. So there are many different posiforms that will map, that will describe the same mapping from a high-dimensional Boolean set to the reals. And it is always possible to find non-negative coefficients, because if you have a negative term, so let's say we have a term to make it concrete, let's say we have a term which is minus 3 times xi times xj, then we can always write this as minus 3 times xi times 1 minus not xj, which gives us minus 3xi plus 3xi not xj, but now we still have something negative here, so I can write this as minus 3 times 1 minus not xi and now we still have minus 3, and I think the statement here was exaggerated, so all coefficients except a0 must be non-negative. A except a0. Okay, and then these terms here would have to be added up. Presumably I have other contributions of this form, let's say of xi not xj, and they would have to be added up. But anyway, you can always find non-negative coefficients in this way. So this was representation number 2 in terms of a so-called posiform, and representation 3 is simply in terms of a polynomial. So for a polynomial, I now restrict the range of my indices. So when looking here at pairwise terms, I have I going from 1 to n. To n. And then similarly for a triple term, sorry, these are subscripts here. So c, I, j, k times xi, xj, xk, and so on. And then the highest order term, I don't need to sum, there's just a single one of these. So this would be the term that encompasses all random variables There we go. So we can count the number of coefficients here. So I had one coefficient plus n over half n over 2 times n minus n times n minus 1 over 2, and so on. In general, these are from the Pascal triangle, or these are the binomial coefficients. So the total number of coefficients which was just the number of entries in the original value table. So this time we have a representation which is unique. Well, this formula here, you can that is so you can look it up, or you can simply remember that these are the binomial coefficients which describe the outcomes, which describe the number of outcomes in n binary experiments, which gives us this number of states. So this is the maximum number of coefficients, but of course many pseudo Boolean functions can be expressed using just a tiny fraction of all of those coefficients. So the maximum total number of coefficients is what I've shown. The actual number of coefficients can be much lower. For example, for this important case of the quadratic pseudo Boolean functions that we're looking at here. For quadratic pseudo Boolean functions, we omit all these higher order terms and have a total number of coefficients which is n squared half plus n half plus 1, which is just the number of entries that I have along the diagonal and along the upper triangle of a matrix. Plus 1 for the constant offset here. And I have a slide here from Frederick Kahl, from a PhD course that he has given, which summarizes how to find these coefficients. It's like solving a triangular system of equations. So first you solve for the constant term, and then you solve for the linear terms, and then the quadratic terms, and so on.